In this video, I want you to learn not only what a molecular formula is, but also how to calculate the molecular formula. A lot of times we'll be calculating the molecular formula based on the empirical formula. First off, let's talk about what the molecular formula actually is. A molecular formula is the actual ratio of elements in a compound as opposed to the empirical formula, which, if you recall, is a lowest whole number ratio. So let me give you an example. Let's pretend that we have the actual ratio of this compound is benzene. It's C6H6. We would call this a molecular formula. However, the empirical formula would be the lowest whole number ratio, which would be just CH. Again, the one on the left here we would call the molecular formula because it's the actual ratio of elements in the compound, whereas the one on the right here we would call this the empirical formula because it's the lowest whole number ratio of elements in a compound. Going back to this specific example, to get from the empirical formula to the molecular formula, we had to multiply all of the subscripts by 6. And in chemistry, this number 6 we call the multiplier. And that's just the number that we're multiplying all of the subscripts of the empirical formula by in order to get to the molecular formula. The equation that we give to the multiplier is the molar mass of the molecular formula divided by the molar mass of the empirical formula. And this should almost always be a whole number, or at least really close to a whole number. Therefore, if you do this calculation and you don't get a whole number, you probably did something wrong someplace. I'm going to put a star by the top number here. The molar mass of the molecular formula is something that has to be given to you in a problem. There's no way for you to guess that by yourself. However, the molar mass of the empirical formula is something that you do calculate yourself. So again, keep in mind that this multiplier should be a whole number. Or at least really, really close to a whole number. Maybe like 5.99, which you would round up to 6 because you need it to be a whole number in order to multiply the subscripts of the empirical formula by it to get to the molecular formula. Okay, looking at the example I gave you, it says show the calculation of the multiplier knowing the empirical formula is CH and the molar mass of the molecular compound is 78.12. So again, we know that the equation is the molar mass of the molecular formula divided by the molar mass of the empirical formula. We also know that this should be approximately a whole number, which we call the multiplier. So let's look at this specific example. Here, the molar mass of the molecular formula. So this top number, which I told you always has to be given to you in the problem, is 78.12. It tells us that the molecular formula is CH, so we need to calculate out this molar mass of the empirical formula. And with an empirical formula of CH, that's just one carbon, and we're going to add that to one hydrogen. So one carbon is 12.01, one hydrogen is 1.01, which gives us 13.02 for the molar mass of the empirical formula. So let's go ahead and plug that in, 13.02. And when you actually divide these, you get the number 6. And in this case, it's exactly 6. And we knew that this had to be a whole number. So our calculation is probably correct. So the multiplier is 6. Once we know what the multiplier is, we can go ahead and multiply all of the subscripts of the empirical formula by that number. So right now it's CH, which is the same as C1H1. And we want to use this multiplier of 6, which means we're multiplying all of the subscripts by that multiplier. So our molecular formula is going to be C6H6, even though it didn't ask what the molecular formula was. And again, the multiplier here was 6, and we use that to come up with a molecular formula from our empirical formula, which was right here. If you're a procedural person and need steps to do this, step 1 would be to determine the empirical formula, and sometimes you'll be given the empirical formula in the problem. Step 2 would be to determine the multiplier. And then step 3 for coming up with a molecular formula is to multiply the subscripts of the empirical formula by the multiplier. And that's it. Just those 3 steps will take you from the empirical formula to the molecular formula. Okay, the example I gave you here says an oxide of chromium is found to have 68.4% chromium and 31.6% oxygen. The molar mass of the actual compound is 304 grams per mole. What is the formula of the actual compound? So step 1 says that we need to figure out the empirical formula first. And remember the rhyme that I gave you in that empirical formula video, which was percent to mass. So we're going to convert these percentages, 68.4% chromium, into a mass, which is 68.4 grams of chromium, and 31.6% oxygen into 31.6 grams of oxygen. And the next step was mass to moles. So let's convert these masses into moles. And using our dimensional analysis here, grams of chromium would be on the bottom, moles of chromium would be on the top. And keep in mind that this conversion factor right here is always called molar mass. Anytime you have moles over grams or grams over moles, that's molar mass. And if you look on the periodic table, the molar mass of chromium is 52.00 grams per mole. And doing this calculation, I got out the number 1.32 moles of chromium. Let's do the same with oxygen. So grams of oxygen on the bottom, moles of oxygen on the top, and again that's our molar mass. The molar mass of oxygen is 16.00, which we could get from the periodic table. Also remember that the molar mass always goes with the grams, wherever the grams is. In this case the grams was on bottom, so that molar mass number went on bottom. Also keep in mind that anytime we have molar mass as a conversion factor, the number that goes in front of moles is always a 1. So doing this calculation, I got out the number 1.98 moles of oxygen. So right now we had 1.32 moles of chromium and 1.98 moles of oxygen. And remember, right now our formula looks kind of like this. And we've done the percent to mass, mass to moles. The next step is to divide by small. So we're going to divide both of these by 1.32. And that's going to give us chromium 1 and oxygen 1.5. So that's the divide by small. The last line in our rhyme is multiply till whole. And because we have a half number here, we're going to go ahead and multiply both subscripts by 2. So multiplying these subscripts by 2 to give us whole numbers is going to give us Cr2O3 for our empirical formula. So our empirical formula is Cr2O3. Now we're going to need to use this information to come up with a molecular formula. Step 1 was coming up with the empirical formula. Step 2, remember, was coming up with the multiplier. So we need the molar mass of the molecular formula, and then we need to divide that by the molar mass of the empirical formula. And remember that the molar mass of the molecular formula has to be given to us. In this case, it's 304. So that's 304.00. And the molar mass of the empirical formula, remember, we figured out the empirical formula to be Cr2O3. And I'm calculating out here a molar mass of 152. So I'm going to put 152 right there. And that's going to give us a number that is approximately 2. So that's our multiplier. Our multiplier is 2. Now from there we're going to take the subscripts and multiply it by the multiplier to get us our molecular formula. So multiplying the subscripts by 2 is going to give us Cr4O6. So that is the molecular formula, Cr4O6. Okay, and the next problem I've given you, practice problem A, it says a compound with an empirical formula of C2H8 N has a molar mass of 46 grams per mole. So the molar mass of the molecular compound is 46 grams per mole. And let's figure out the molar mass of this empirical formula. With 2 carbons, that's 12.02. With 8 hydrogens, that's 8.08. And then 1 nitrogen is 14.01. And if you add these all up, you get 46.11 for the molar mass of the empirical formula. Now let's figure out the multiplier. That's going to be 46, which is the molar mass of the molecular formula, divided by 46.11. And if you divide these out, you'll get approximately 1. So in this case, our multiplier is 1. And what that means is that the empirical formula and the molecular formula have the exact same formula. So the empirical formula for this compound is C2H8N, just like the empirical formula was. Okay, let's look at that second example now. In that second example, it says, what's the empirical formula of a molecule that contains 18.7% lithium, 16.3% carbon, and 65.0% oxygen? So remember, we need to figure out the empirical formula first. We're going to change this to 18.7 grams of lithium, change this to 16.3 grams of carbon, and this one to 65.0 grams of oxygen. Now let's determine the number of moles of each thing. That's 2.69 moles of lithium. .36 moles of carbon, and then I'll try to squeeze this in here. 65.0 grams of oxygen, 16.00 grams of oxygen with 1 mole of oxygen. That's going to be 4.06 moles of oxygen. So to recap here, I have 2.69 moles of lithium, 1.36 moles of carbon, and 4.06 moles of oxygen. So right now my formula looks kind of like this. And the next step is to divide all of these subscripts by the smallest one, 1.36, 1.36, 1.36. That's going to leave me with Li2C1, and since we don't write the ones, I'm not going to put the 1 there, and then O3. So Li2CO3, which is lithium carbonate, is the empirical formula. Now the molar mass of the empirical formula is 73.89. And that's grams per mole. So for the multiplier, it tells us the molar mass of the actual compound was 73.8. We're dividing it by the molar mass of the empirical formula, and that gives us about 1 for the multiplier, which, remember, just means that the empirical formula here and the molecular formula are exactly the same. So the empirical formula is Li2CO3, which is lithium carbonate.